So I'd like to talk about the classification of Heegaard splittings, which is work with Toby Colding and Dan Ketover. So let me give you a little bit of background. So a Heegaard splitting is of a three manifold. So unless said otherwise, three manifolds will be closed and orientable and irreducible. Irreducible means you can't split along a two-sphere and get sort of two interesting pieces. So a three manifold, well, a closed three manifold can be obtained by gluing two handle bodies together along their boundary. So a handle body is simply just a solid torus, solid surface of genus G, and just gluing such a thing along the boundary. So such a decomposition of the three manifold is called a Heegaard splitting. So it's sort of amazing that three manifold is such a tremendously rich subject, but the pieces are sort of just so simple. So therefore, it's somehow reflecting the richness of the gluing maps. So in particular, the three sphere can be gotten by gluing two three balls together. And S2 cross S1 is gotten by just taking a solid torus and doubling it along its boundary. Right? You can see just a meridional disk. When you double it, it's a two sphere, and then you get sort of an S1's worth of them. And the lens spaces are the spaces obtained by gluing two solid tori together. So basic fact in three manifold topology is that every three manifold has a Heegaard splitting, and the proof, I guess, goes back to Moise, who showed that every three manifold is triangulable. So it can be built by just gluing three simplices together. So three simplices together. So therefore, if you have a triangulation, then you can take a neighborhood of the one skeleton, which is clearly just a solid handle body. And on the other hand, if you look at the dual one skeleton, a neighborhood of that is also a handle body. And so, but the manifold is built up by just its neighborhood of the one skeleton, neighborhood of the dual one skeleton. So just automatically from a triangulation, you get a Heegaard splitting. So here's the classification problem, which is given a three manifold, to list without duplication all the irreducible Heegaard splittings up to isotopy. So if you have two splittings, well, I mean, if you just do an ambient isotopy in the space, well, let's just consider those the same. So first, there's a little technical point of exactly what do we mean by Heegaard splitting. Well, I sort of said it's sort of just a decomposition of the manifold into just gluing things together, but there's actually slightly different ways of thinking about this. So for the purposes of this talk, let's think of a Heegaard splitting as actually an ordered pair. I mean, there's a splitting surface, but we know the first, one side, the other side. So said another way, a Heegaard splitting corresponds to sort of a splitting surface together with, say, a normal orientation pointing from the zero side to the one side. So that's what we mean to say to classify up to this. But I mean, if you forget about the side in this, you just a similar discussion will entail, and also you could just talk about equivalence up to homeomorphism. Is there a homeomorphism in the space? It takes one surface to the other. So that's one thing. And the second thing is just to recognize that if you have a Heegaard splitting, well, there's there's essentially a trivial way of just creating one of genus higher. So it's already in the context of the three-sphere. We could just glue three balls together, but if you just take a three ball and just drill out, say, a unknotted arc, well, then you get a solid torus. But then what's left is then, well, the stuff that you drilled out. So it's a sphere with a handle. So there we go from like a genus zero splitting to genus one. And more generally, if you have, some complicated, splitting, well, you could just off in the corner somewhere just add on a little handle, and that could just raise the genus by one. And so this operation is called stabilization, and the other operation of just removing sort of a trivial thing is called destabilization. So I mean, since we're talking about irreducible three manifolds, then a Heegaard splitting is said to be irreducible if it can't be destabilized. And a classic fact that goes back to the 30s independently by Reidemeister and Singer is that if you take any two Heegaard splittings, then if you just add enough trivial handles to one side and add enough trivial handles to the other, then become sort of isotopic. And that's sort of an analog of fact known earlier is that, well, at least in dimension 3, is that any two triangulations can become isotopic after suitable subdivision. So the question here is up to to find the irreducible splittings up to isotopy. So before we get there, let me just for some background and just to get an idea of sort of the richness and of the subject, here's some highlights of the theory. I mean, there's just a huge literature on this, and here's some basic facts. And the first is that, well, Waldhausen showed that the three-sphere has a unique Heegaard splitting. Again, we're talking about up to isotopy, and here actually slightly stronger is that any splitting is just a stabilization of the trivial one. And Joan Berman was the first, I believe, to show that there exists a manifold with two different splittings. And in this case, she distinguished in the lens space the torus sort of with one normal orientation versus the other. Somehow, for certain lens spaces, you can't sort of isotope one to the other. On the other hand, if you just ignore this sort of sidedness that independently Bonal and Ertal and Hodgson-Rubinstein showed that lens spaces have unique Heegaard splittings. And, well, in the course of various works in the 90s, there's this work of Yoav Moaya, Jennifer Schultz, Martin Lustig, and Sedgwick that for ciphered fibered spaces they have sort of they enumerate all the possible irreducible splittings, and except for some very rare circumstances, they can show that they're all distinct. And, well, I'll say more about this in a moment, but in particular, Johansson, in the case of Hawken manifolds and Taulian for non-Hawken, showed that the following finiteness statement, which answer a conjecture of Waldhausen, which is, well, Johansson showed that if you have a Hawken manifold, then if you look at the splittings of minimal genus, that is, you look at the minimal G such it has a Heegaard splitting of genus G, and then you look at all possible splittings of that genus. Well, then there's only finitely many, or at least up to spinning about a torus. So if you have a torus, then you could sort of there's a homeomorphism by just cutting the torus and just doing like a Dane twist across S1, spinning around the torus. So up to that, there's only finitely many splittings of minimal genus, and Tao Li showed that for non-Hawken manifolds, that's it. There's only finitely many minimal splittings. And so that answered the Waldhausen conjecture. And sort of in a different direction, so this remarkable work of Haas, Thompson, and Thurston, and independently Bachmann, found example where you have a manifold with genus G splitting, and it takes G, well, for Haas, Thompson, Thurston, and Bachmann showed G minus 2 stabilizations for those things to be isotopic. So these splittings are actually quite different because it takes quite a number of stabilizations to become isotopic. And I should remark, this is really quite a remarkable theorem because it's done 2007, and after all, Reidemeister Singer 70-something years earlier said that it takes some number of stabilizations to make any two splittings equivalent. And in the intervening 70 years, all the examples that were known, it only took one stabilization to make two different ones, say of the same genus, to be equivalent. And suddenly it takes a lot of them. So this is sort of a very interesting question in general. Well, this work of Caston and Gordon, 1987, played a big role in the subject. They introduced this idea of strongly irreducible Heegaard splitting. So remember, Heegaard splitting is taking two handle bodies and gluing them together. And something strongly irreducible if you look at a compressing disk on one side and a compressing disk on the other, then the boundary has to cross each other. So therefore, if the splittings of genus a million, these disks on each side have to be very complicated to be able that every one on one side intersects every one on the other. Oh, yes. So if you have a handle body, that's simply just a disk, a central disk with. So it's just that's what I call it's a compressing disk. So right. So they introduced this idea of strongly irreducible Heegaard splitting, and they proved this sort of remarkable theorem, which is that in the non-Hawken case, for non-Hawken manifolds, that irreducible splittings are also strongly irreducible, and that was actually quite striking. And the second thing is they exhibited a hyperbolic manifold that had infinitely many different strongly irreducible splittings, in particular infinitely many irreducible Heegaard splittings. And that was quite remarkable because at that point, well, up to spinning around tori, as far as I believe this was the first example where you had sort of infinitely many different things. So, I mean, since we're in Princeton, I'd like to take sort of a human interest interlude. So this guy Richard. So this part C is used essentially. The PhD thesis of Richard Paris, and well, let me just leave it at that. But I went to Richard Paris's PhD defense, and that was in 1978, and that was like the first and last time I saw him, at least that I'm aware of, and I never heard about him since, and I could only speculate what happened until 2 days ago, where I discovered that Richard Paris had sort of a spectacular career as an educator. I mean, it took him 11 years to get his PhD, but I think that's more reflection of the Vietnam War was raging, and for technical reasons, there'd be reasons people wouldn't want to finish their degree, and in particular, at the time, Princeton only supported graduate students for 3 years. So he was working at various colleges to support himself in that period. But after he got his degree, he basically spent the next 30 years at Phillips Exeter Academy, and he apparently had just in many different dimensions, of which I mentioned 3 here. He seemed to just be spectacular and inspiring people in many different ways. In particular, he won from the NSF the 1991 Presidential Award for teaching. So back to classification of Heegaard splittings. So I mentioned the work of Johansen, Tao-Li, and I'd like to discuss this in more detail because, in fact, Johansen's theorem is a bit stronger than I stated, and Tao-Li proved sort of a series of really remarkable theorems. And in particular, Johansen showed that if you have a Hawken manifold and you fix a genus, then there's a constructible set of genus G surfaces, finite set, so that up to spinning around tori, every irreducible splitting is one of those. And on the other hand, in the non-Hawken setting, in a series of 2 papers, that Tao-Li showed that for every genus, then there's only finitely many Heegaard splittings, irreducible Heegaard splittings of that genus. And furthermore, he gives a way of constructing a finite set of Heegaard surfaces so that every Heegaard surface that's irreducible of genus G appears in that list. So as I mentioned in the beginning, that if you have a triangulation, then basically the genus of the one skeleton gives you an upper bound for the genus, and for every genus, that and below, that's a finite set. Tao-Li can tell you whether there's an irreducible splitting, Heegaard splitting or not, and so therefore this gives an algorithm to compute the Heegaard genus of the manifold. And further, generalizing this 2005 paper, he showed that there's some finite number n, so that any irreducible Heegaard splitting of this manifold has genus bounded above by n. So in particular, there's only a finite, for non-Hawken manifold, there's only finitely many Heegaard splittings. So these are strong generalizations of Waldhausen's conjectures, and I should say these are really deep theorems. I mean that Johansen's, he wrote this 426-page book of which had various things, but this was sort of the main theorem, and Tao-Li's in total these are about 150 pages of hard work and quite remarkable. So in particular for non-Hawken manifolds, you have to push it a little further to do a classification theorem. So in particular, what exactly is missing to give a sort of a complete classification? Well, there's 3 things. The first is that the fact that there's an upper bound is an existence theorem, and you need to be able to produce, at least in finite time based on the original data, sort of a number. And second is that the surface, the Heegaard splittings in Tao's list might have some duplicates, and third is there might be some splittings in the list which are reducible. So here's the the main theorem I want to talk about today, and that is if you have a closed non-Hawken hyperbolic three-manifold, then there's a, with Toby Colding, then we have a solution to one, finding effective algorithm for computing this upper bound. And with, well, in addition, with Dan Ketover, we have a way of weeding out the duplicates and reducibles. Now, I should point out that Tao Li's work is amazing because he did this all by bare hands. I mean, just but sort of in the intervening period, Perlman appeared, and we have sort of geometrization. So in the non-Hawken manifolds, therefore there's this. I mean, they're either the hyperbolic or ciphered fibered, and so to, well, I mean, there's a lot of work of Yoav and his collaborators in this ciphered fibered. So we're addressing the hyperbolic, and so hyperbolic manifolds come with tremendous advantage. The fact that you have this metric of constant -1 curvature, and that's, as you'll see, that will play sort of a big role. And so the hyperbolic structure together, just using some fundamental ideas from Tao Li's work, that's sort of, you see what's behind sort of these two things. So there's also another key theorem which is essential, which is due to Pitts, Rubinstein, and Dan Ketover, which is that if you have a hyperbolic three-manifold, so you have this metric of constant one curvature, and just do this, perturb it generically, then any strongly irreducible Heegaard surface is isotopic to one that's either an index at most one minimal surface, or it looks like, well, a one-sided surface, and if you just take a little two-fold cover and then just put a little tube, then it's constructed that way. Or said the other way, you could just pinch a tube and the thing just collapses down to a one-sided surface. So, so corollary of that, which is a function of bumpy metrics, is certainly these guys knew in the 80s, is that such a metric only supports finitely many minimal surfaces of a fixed genus. So in particular, there's this sort of non-effective but just finiteness statement that non-Hawken manifold has only finitely many irreducible splittings of a fixed genus. So, as a matter of disclosure, the fact is that unfortunately Pitts and Rubinstein never sort of wrote down their proof, and Dan Ketover in the last couple of years have he's proven this statement sort of modulo the index bound. I mean, it's this index of so a surface is sort of index 0 if, so a minimal surface is one that's locally area minimizing, a really tiny disk, small perturbations. You can't reduce area if you fix the boundary. A stable surface, index 1, is that you can't do any global perturbations and reduce area. Sort of index 1, in some sense, you could just sort of perturb in sort of one way or the other, and it's sort of. So I'll say more about that in a moment. So anyway, so as a matter of disclosure, is that, well, I saw Chaim in Brazil in January, and he says, well, he has his notes on somewhere, and he hopes to write it up someday. So it's So remember that we're trying to prove. I want to just show you sort of what are some added ingredients to prove one. So let me try to explain that. So first there's this theorem well, with Toby, but sort of the core hardcore work is due to other people, Shane, Lopez Ross, Chang Tisks, and multiple papers of Colding and Minicozy. And that says that if you have a hyperbolic three-manifold, then there's finitely many branch surfaces that carry all minimal surfaces of index 1 and all strongly irreducible Heegaard splittings. So these branch surfaces, well, are what we call eta negatively curved. So, well, I'll say that in a moment, but just to start with, a branch surface is simply just a 2 complex where, well, locally either it just looks like a surface or maybe 2 surfaces coming together, and they're coming together tangentially and smoothly along this branch locus, or you might have locally 3 that are coming together, in that manner. So therefore, these are, well, just smooth surfaces that are sort of glued together smoothly. And eta negatively curved means that if you have a little surface that's sort of carried by the branch surface, that is, it's lying close and tangent to it, then that surface, its intrinsic curvature is, well, eta or less. So you can think of it's almost -1 or more curved. So the point is this, is that Rick Shane showed that, at least in the context of hyperbolic three-manifolds, but much more generally, is that if you have a stable surface, stable minimal surface, then there's an upper bound on the second fundamental form. In other words, the surface can't have too much curvature. So if you have surfaces that their curvature is sort of bounded, then you could, well, you can find just locally, just a finite number of pieces that more or less any surface is more or less tangent to approximately locally, and then you put them all together. So if the manifold, for example, is given to you as a hyperbolic manifold with a, say, totally geodesic triangulation, then locally you could just effectively just build all these pieces. Now, see, here's the index 1 thing, is that if it's index 1, there might be some spot where there's high curvature. And again, a series of papers of Colding and Minicozy said that if the curvature is sufficiently high, then it all occurs in one spot, and it looks very close to a catenoid. So therefore, therefore, if you look at the totality of surfaces that are index 1 or index 0, then they pretty much look like surfaces that don't have much curvature, or there's some spot where there's a catenoid. So therefore, we construct like the first set of things, and then put little catenoids in little spots. So this is sort of the idea of this theorem. And the second ingredient is this.
Dave, can I ask?
Yes?
So minimal surface, your hyperbolic three-manifold is constant sectional curvature -1?
Yes. So
minimal surface will have strictly less than -1 curvature?
Yes. So these things could have curvature at most -1 plus epsilon, and could be sort of more negatively curved. But they can't be too negatively curved because of this sort of the Rick-Shane curvature bound. So
I'm just confused by your eta there.
Yeah, so eta means that the intrinsic curvature is at most eta, but the fact is that at most eta, but in fact there's going to be some other bound on the other direction.
When you say the surfaces are carried, is that a geometric notion of?
So it's just like a train track where so carried means if you just take a very thin neighborhood, then any surface lies in a very small neighborhood of one of these branch surfaces, and the projection is approximately just a nice projection. Yeah, that's right. So So yeah, so these things are two-dimensional. Of course, in surfaces you could have like multiplicity of just copies. So it's a projection. So it.
You can have a number of leaves in this.
Yes, definitely, yes. So then there's a second ingredient, which is, well, we stayed in the context of branch surfaces, but it's really 99% due to Joe Plant. And Joe Plant proved in this sort of 1975 Annals paper, sort of remarkable theorem that if you have a foliation, which has a transverse measure of full support, then any leaf grows. Well, the growth rate of the leaf is bounded polynomially, and this is really actually extremely simple. I mean, it's this beautiful idea, which is that here's the idea. I mean, the fact is that, imagine like on the context of a say a surface of genus 2, and here's the little fact is that the number of elements of H1, H lower 1, that are represented by curves of length L, that just grows like polynomially, maybe quadratically in the length. And the point is that if you have a surface of genus 2, there's two curves so that two essential curves, and the fact is, just by duality, we know that any curve in H1 is determined by its algebraic intersection number with these curves. So if the curves are separated by 1, say distance 1, then if you have a curve of length L, it can hit those things geometrically at most L times. Or algebraically most L times. So therefore the element of H1 it represents is like A1 times this plus A2 times that, and A1 plus A2 is at most L. So in the same manner, if you have just a 3-manifold, the number of elements of H1 sort of grows polynomially in sort of the length of the curve. And on the other hand, if you have a surface that's carried by this branch surface, or more generally, in a foliation, then if you just look at a little chart, actually first you should just pass to a twofold cover so that the normal orientation is just consistent across. It's sort of transversely normal orientation to the surface is consistent everywhere in the branch surface. So the point is, it really amounts to just showing that if you look at a typical transverse arc, that there's only polynomial number of times that it intersects this thing. But the point is, every intersection, you could think of this surface as like a cohomology class, and if you have a curve in this surface, and it sort of goes around and comes back, and then you take a little transversal. So you could a little count of algebraic intersection with that surface. So anyway, the point is that more or less the intersection number with a transversal is corresponds to different elements of H1. Anyway, that's the key point. So here's what you might ask: what does this have to do with Heegaard's splittings? But the corollary of these two facts is that there's a computable number, so that if a surface is carried by one of these branch surfaces, then the injectivity radius of the surface is uniformly bounded above. And the point is that hyperbolic surfaces, their area grows. A hyperbolic plane, its area grows exponentially in the radius. On the other hand, exponential is a lot bigger than polynomial. So after a bit, there has to be sort of, the surface has to come back to itself. So there's a uniform bound on the injectivity radius. And anyway, that turns out to be sort of the crucial point for bounding, for getting this sort of effective upper bound on the Heegaard genus, because anyway, I totally suppress the technicalities, but a lot of work involves with splitting branch surfaces and keeping track of things, but because of this injectivity radius bound, you only have to do these things sort of a finite amount. So anyway, so these are the two really new ingredients for the proof of this effective finiteness of the upper bound. So, I should have shown you this picture before. This is a way of popping in a catenoid. So if you have like a little smooth surface, then you could do this sort of Dangerois splitting operation. Just put a little bubble in the surface, and then just pop in a catenoid, and that's how you put a little local catenoid in the branch surface. So.
Sarah, could you walk your hands over that bottom picture and show us where the surface lives and where it isn't?
So here's this little catenoid, and its tangent. So here's this bubble, and right along this curve over here, it's coming in sort of. Here's the surface. It's the catenoid sort of coming in like this. Just rotate it around, and the bottom of the catenoid is coming in tangentially to this sort of bottom surface.
You expect that catenoid to just have multiplicity 1 with respect to the...
I think so. I think you can assume it's just multiplicity 1 because assuming it's index 1. Okay, so now I'd like to give you a hint as to how to decide whether two Heegaard splittings are isotopic. So to start with, suppose we had two Heegaard surfaces, and the question is, are they isotopic? And because after all, I mean, tau just gives us a finite set of Heegaard surfaces, and we need to know whether they're isotopic or not. So there are these surfaces T0 and T1. So, well, T0 and T1 extend, I mean, just by filling it in. There's a handle body on one side, handle body other, so it fills into this nice foliation called a Heegaard foliation. And same thing for T1. And, well, the fact is that if T0 is isotopic to T1, then there's an isotopy of the first Heegaard foliation to the second. And actually, that's a little trickier than you might think, but the fact is just the first approximation, just the isotopy of T0 to T1 gives a, well, by isotopy extension, an isotopy of the handle bodies, and then, well, up to certain operations, the one complexes are the same, and actually, well, even if you have two products, surface cross I, and you have two different foliations, product foliations that agree near neighborhoods of the boundary, I mean, it's actually a deep theorem of Ladenbach and Blank that you can actually isotope one to the other. But in any case, in summary, if they're isotopic, then you could actually just get this isotopy of Heegaard foliations from one to the next. But allow me to point out that so each vertical line corresponds to a Heegaard splitting, and on one side there's sort of a one complex at one end and one complex at the other, and so going from here to there, there's like movement of one complexes. Here's two things coming out of the one complex, and arcs might slide along, and there's sliding edges over edges, and so on and so forth. So here, in my opinion, why this is sort of a challenging problem of deciding this isotopy business, whether things are isotopic. I mean, let's think in terms of the surfaces themselves. I mean, the fact is that getting from T0 to T1, it might require that you have to go through some incredibly complicated surface to get from in the isotopy from T0 to T1, you might have to pass through some really complicated surface. And maybe by complicated, that means that the area might be enormous. On the other hand, well, okay, there's more or less a transformation, a passage of a one complex on the left to the one complex on the right. And well, a little neighborhood of a one complex doesn't take much area, but the complexity there is that, well, maybe the length of the of the arcs in the one complex might be extremely large. So there's sort of this duality of problems. I mean, to get some way from T0 to T1, well, with bounded area, but on the other hand, you don't have like spots in the surface where there's sort of like thin necks. In other words, you want to be able to get from T0 to T1 in the world of some bounded geometry, where bounding the area above and bounding sort of the diameter of an essential curve from below. So if you could do that, well, you might think there's some hope that, well, and there is, that in the world of such surfaces you can, well, there's some finiteness statement. So yes?
Are you picturing the one complex as saying setwise fixed?
No, the one complex is actually moving along by, sliding of you're allowed to, slide the edges over vertices. So, I mean, just the usual thing, right? I mean, that if you have, this guy here, then you can, slide him to there.
Sure, but so if you look at a little neighborhood of those
So a little,
picturing that?
so a little neighborhood. I mean, they both have sort of, isotopic
Right.
neighborhoods.
So you're picturing a little neighborhood and staying sort of in place.
Well, I mean, in the right near this, say the top. I mean, this process is sort of like the whole thing is sort of like moving. So if you ignore this curve, then the surfaces are moving, although they're in the limit. This arc is moving over there. So right. So at this moment we have this sort of this isotopy of foliations. So here's this remarkable thing: is to generalize the Almgren-Pitts min-max theory to 2 dimensions. So here you have this square of mappings of a surface into the 3-manifold, where in the left is the original Heegaard foliation, the right is the original one, and the top and bottom are maps of 1 complexes. So the thing is, what we want to do is just pull out all this stuff in the middle and put in sort of a new system of surfaces. So this H is a map from surface cross I into M. It's called a 2-parameter sweep out, and has the property that, well, it has the same restricted boundary behavior, but the area of all the surfaces in the middle have area uniformly bounded above, where the uniform bound is, well, the area of the surfaces in the left and right Heegaard foliations, and 2 pi plus some arbitrary epsilon times the Euler characteristic of the surface, or the absolute value of the Euler characteristic. So, but the beauty of this is that somehow we started originally with these Heegaard foliations, and then we just sort of forget about it. We just fill in with this square of mapped-in surfaces, where each surface is embedded, and they're, at least in the interior, they're varying smoothly from one to the next. So here's sort of so once you've got that, here's sort of the key picture of finding this.
Wait, so can you go back 1 slide?
Oh, yeah, sure.
C, so that's a theorem there. C is determined by the initial data.
Yes.
Okay.
So once you have that, here's how to find this bounded geometry isotopy from T0 to T1. And the thing is, if you look at, remember, right at the top is sort of all along the top are 1 complexes. So this red region is this set of regions where if you have a point in the red region, you have a surface, an embedded surface in the 3-manifold. And it's a red point if you could find a curve on that surface of sort of small diameter, where small is some small number fixed delta relative to the projectivity radius of the 3-manifold, which sort of compresses to the H1 side. And the green is are the surfaces that have curves that go to the H0 side. And the point is that you can't have any point that's both red and green, because if you had a point that was both red and green, that would mean that there's some really tiny curve which compressed to the red side and some really tiny curve which compressed to the green side. And if those curves were sort of disjoint, well, that would contradict strong irreducibility. And if they were like really close, well, then they lie in some ball, and you could find some curve on the boundary, and one of those curves in the inside, again, which will violate sort of strong irreducibility. This condition of strong irreducibility guarantees that the red region, the green region are disjoint. So therefore, we can sort of thread a path from the left to the right. And so the fact is, by this step 2, all the surfaces in between have bounded area. And by this construction directly, they have this lower bound on any curve that contracts to one side or the other has diameter bounded above. So right. So anyway, so this is, there's some technicalities here, but this is the point, is that if you look in the world of surfaces that have bounded area and also a bound on the diameter of short curves, well, then that's there's sort of like a finite net within such surfaces. So the point is, if you have, well, do I give it a construction? Well, anyway, so you can build a finite graph where vertices correspond to surfaces of bounded area and this bounded, call it diametric sol, and two vertices are connected by an edge if they're sort of close in some measure. So actually, for technical reasons, this at this moment we're acting in a smooth category, but for technical reasons we work in the piecewise linear category. So the surfaces of interest are what we call crudely normal. So so if you have a triangulation and you have a surface transverse to the one skeleton, then and maybe the two skeleton too, then it's crudely normal if the restriction to each simplex is a union of disks, and it's crudely almost normal if there might be one annulus. So anyway, so this G is, the vertices are crudely normal surfaces with respect to a certain triangulation of uniformly bounded weight, and the edges correspond to these crudely normal surfaces that differ by some elementary isotopy. And here these pictures show like an elementary isotopy. So right here, this is, this stuff is part of the triangulation, and there's part of the surface. So if you just move the surface up, that's what we call sort of one elementary move, and then there's a few others corresponding to one simplices and two simplices. So anyway, so that was sort of a brief discussion of how to decide whether the two things are isotopic. And so here's the question: how do you decide whether a Heegaard splitting is reducible? So in this case, well, so you can imagine, here's this complicated manifold, and here's the surface, and as far as you can tell, it looks irreducible. But the fact is, if it's reducible, then there's some isotopy which just isotopes that surface to one where there's, off in the corner, there's this tiny, obvious destabilization. So in particular, if you just start with your, if it's reducible, then there's the original Heegaard foliation, and then there's a new Heegaard foliation where every leaf in that foliation has curves that are really small that compress to both sides. So now it comes to staring at this picture, where we're here. Here again, we have this. Again, we sort of we do this sort of two-parameter min-max thing to fill in this square with two-parameter family of surfaces of bounded area, and here on the left was original Heegaard splitting, and the one on the right is this Heegaard splitting with surface T1, where it was sort of obviously destabilizable. So here when you're all the way on the right, there's curves that look really small to the that compress to the left and very small that compress to the right. So that what you're supposed to get out of this picture is that, well, there's some number, like it's called, well, delta, where things on the right, everything compresses. There's delta short curves on every leaf that compress both to the right and to the left. But on the other hand, there's some surface J with the property that you can get from T0 to J by a path where no curve on that path is short from the point of view of either the left, the 0 side, or the 1 side. So, right. So this is good because, if your vision, if you can only see out the distance delta, then as far as you can tell, everywhere along that path, this surface looks incompressible. But on the other hand, if you put on like new glasses and you can see out to 2 delta, then if you're like in this sort of, if you can see out to 2 delta, then this surface J, looks distinctly reducible. So, right. So again, we construct the same graph as before, where the vertices were these like crudely normal surfaces of bounded weight, and the edges were the surfaces differed by sort of elementary move. And the point is, certain of these vertices correspond to surfaces that are obviously reducible. And this lemma showed that if you have your original Heegaard surface, then it's in the same path component of this finite graph as an obviously reducible one. So, there's certain technicalities here, but the thing is that we have 2 triangulations. One where the simplices are extremely tiny, and so from those tiny simplices, if you sort of look out might be like look at the second star or something in the simplex. As far as you know, like these surfaces just look, you don't see any things coming around, so they just look perfectly, they look incompressible as far as you can tell. But on the other hand, if you look at the scale of, say, 2 delta from this, there's this triangulation delta 3 where any 2 delta diameter set is contained in its second star, or maybe its first star, and the second star is a 3-ball. So the point is that in with that triangulation, you could look at kind of some reasonable distance, and you can decide, give enough vision to decide whether it's this Heegaard splitting is reducible, because you can see small compressions to the left and to the right. So right. So this understanding this reducibility question is denoting that at the scale of delta 4, all surfaces in this isotopy from T0 to J looked incompressible, but you can test reducibility using the scale of delta 3. So anyway, so that's sort of a hint of how to weed out duplicates and reducibles. So let me just say that this theory of Heegaard splittings, I think, is really interesting, just intrinsic topologically, but also because there's so many different sort of techniques and ways people look and approach this, and there's still sort of a lot of very interesting questions that are in the subject. So in particular, I mean, this work was all done in the world of non-Hawken manifolds, but there's still sort of, it still needs to be sorted out in Hawken manifolds. I mean, in the same manner that Tao Li gave us this list of surfaces which contain all of a given genus, that contain all the irreducible ones. I mean, so does Johansen, but sorting out the duplicates and reducibles there needs to be sorted out. And second, there's and also there's still interesting things in the ciphered fibered world. And the second is there should be some generalized Waldhausen conjecture for Hawken 3 manifolds, and I think it's versions of this are sort of implicit in various works of that there should be some question in Tao Li and work of Mariah Schleimer and Sedgwick that but here's maybe a question, which is, if you have a Hawken manifold, is there sort of a finite, say it's Hawken atoroidal, is there some finiteness theorem in the sense that, well, there's maybe a finite number of Heegaard splittings, but then there's a finite number of such that, well, okay, we know there's an infinite number of Heegaard splittings, but any one could be gotten from the finite one by this finite collection by just picking one there and taking some incompressible surface and doing some Hawken sum. So I should mention that independently, Tao Li and Mariah Schleimer Sedgwick studied these Casson-Gordon examples, and they showed that they were all this form. And more generally, in the non-Hawken world, I mean, using Reidemeister-Singer, the fact is any two Heegaard splittings are equivalent up to stabilization. So there should be, it would be very interesting to be able to actually just find a theory, to be able to, given a 3 manifold, to be able to just produce the tree of Heegaard splittings, this finite tree coming from stabilization. So as I mentioned, a special case of one, there's still some special cases, duplicate question to be sorted out in the work of Yoav Mariah and Jennifer Schultens and their collaborators. And 3, there's this, well, in some sense, this is this question about branch surfaces that, if you wanted to put some of this stuff, in particular one, in a purely combinatorial setting, well, you can do that if you can solve this purely topological question about branch surfaces, where if you have a branch surface in a compact irreducible atoroidal 3 manifold, can you, in some effective way, in finite time, just produce a finite set of other branch surfaces which carry no spheres or tori, where these other surfaces, the property that if the original surface carried either an irreducible Heegaard surface or an incompressible surface, it would be carried by one of these other surfaces. And if you could do that, that would at the combinatorial topological level would really clarify a lot of things. Anyway, thank you for your attention.